Swayam Prabha. Digital India. Educated India.
I welcome you all to the 12th lecture on the topic multi-stage air compressor. So, in the previous lecture number 11 also we have discussed about the air compressor, but it is of single stage. So, in the previous lecture let us have a quick recap. We have seen the construction of a reciprocating air compressor, how the compressors are classified. The broad classification is positive displacement and the dynamic one. So, in positive displacement we have the reciprocating air compressor. We derived the work of compression for a reciprocating compressor without clearance first and then with clearance volume. In practical all the compressors would be provided clearance volume when they design the compressor. So, there will not be compressor without clearance volume. We have solved the numerical questions based on the work of compression for various processes such as isothermal process, isentropic process and polytropic process. Polytropic process is PV power n equal to constant, where n is less than gamma. Isentropic process is PV power gamma is equal to constant, that is PV power 1.4, gamma is equal to 1.4. And isothermal process is the constant temperature process, PV equal to constant, where n is equal to 1 in the equation PV power n. In the numerical question which we have solved, we found that the isothermal work done is was the least and the isentropic work done was the highest. The polytropic work done is more than isothermal work done, but less than isentropic work done. Now, let us see the contents of this lecture number 12. Comparison between single stage and multi-stage air compressor reciprocating type, two-stage air compressor construction and working, derivation of work of compression for a two-stage compressor, and one numerical question. So, if we look at the comparison between a single stage and multi-stage, as the name indicates, single stage there is only one stage, one piston cylinder arrangement. In case of multi-stage, more than one piston cylinder arrangements are used. So, the first point is single cylinder is used, and in case of multi-stage at least two cylinders would be used, a low pressure cylinder and a high pressure cylinder. If there are if the number of stages are 3, then 3 cylinders would be used. The single stage has drawback of the low volumetric efficiency. So, that is the ratio of actual volume of air that is admitted, or this one, to the theoretical volume of air. This volumetric efficiency is comparatively high for a multi-stage compression compared with a single stage compressor. Losses are more in the single stage compressor, and which is minimized in case of multi-stage compression. Cylinder size is large because we are using only one cylinder, and in this case it is comparatively small. In case of a two-stage compression, smaller size of cylinders are used, 2 cylinders are used. Temperature of the fluid which is compressed, it is quite high, whereas here it is less because a device called intercooler is incorporated between the first stage of compression and the second stage of compression, which we will be seeing in the construction of the multi-stage air compressor. And generally these single stage are used for low pressure ratio applications, and the multi-stage are used for high pressure ratio applications. The objective of developing a multi-stage compressor is to minimize the work of compression, that is the power consumed by the compressor. We have seen in the previous lectures, especially when we are discussing about the heat engines, that is the development of the heat engines pertaining to the Kelvin-Planck statement of the second law of thermodynamics, or the refrigerator or a heat pump which is operating between a source and a sink, which is as per the Clausius statement of the second law of thermodynamics. Any reversible device, whether it is a heat engine or a refrigerator or a heat pump, its performance is better than an irreversible process, that we have already seen. So, in the case of compressor also, if we are able to reduce the irreversibilities, that is due to this friction, losses of heat, all those things and all, then the performance can be enhanced. So, in case of a power producing device, if the processes are reversible, then the power output, the work done by the system, whether it is at, for example, it is at, let us take a turbine. So, if the irreversibilities are reduced, then the net work done by the system, that is the turbine, would be more. Similarly, if the irregularities are reduced in a device like compressor, the power consumed by the compressor will come down, can be minimized. However, there are challenges in when it comes to reducing the irreversibilities, reducing the loss of heat due to friction and other reasons. So, because of that, what they are doing in the multi-stage compression is, the temperature of the fluid after the compression, after the first stage compression, the substance is cooled by a medium. So, the temperature alone is reduced again before it is compressed in the second stage. So, we will see that one in the construction and the working. This is the schematic of a two-stage air compressor. So, as the name indicates, two-stage, there are two cylinders. The one is the one on the left side is the low pressure cylinder. So, this is cylinder number 1 and this is the cylinder number 2, high pressure cylinder. Okay. So, this is cylinder 1 and this is cylinder 2. So, the air is first admitted in the low pressure cylinder through the suction valve, through the inlet valve. So, of course, the valves are not shown, but it will be there. So, air is taken during the suction stroke through the inlet valve in the low pressure cylinder. As the piston moves from BDC to TDC, it is compressed, where the pressure and temperature of the working fluid is increased, it is raised, and the compressed air goes to the intercooler. In the intercooler, heat is removed from the compressed air, bringing down its temperature alone by a medium. So, we can use a coolant like a water. So, the temperature is brought down and the compressed air from the low pressure cylinder, after it is cooled, where its temperature is reduced, it is again circulated to the high pressure cylinder, where it is compressed further and the compressed air is supplied, the compressed air is discharged through the discharge valve. Okay, here also the suction and discharge valve are there, but it is not shown in this schematic. And this air here, which is taken from the discharge valve, it will be supplied to it enters the suction valve of the next cylinder and the compression takes place. And here there is a concept called perfect intercooling and imperfect intercooling, which I will explain in the subsequent slide by using the PV diagram. So, this is the pressure volume diagram for a two-stage compression. Okay. So, here there are three pressures are there. One is the inlet pressure of the low pressure cylinder, that is the air which is taken, then it is compressed P1, P2, and here P2 is equal to P3 theoretically, and it is compressed. Okay. So, there will be P4. So, P2, if you take P2 equal to P3, so this is one inlet pressure, then this is the like an intermediate pressure, and this is the high pressure. So, there are three pressures P1, P2, P3. So, P1, P2, P3. So, the pressure air enters the cylinder at P1 in the low pressure cylinder and it leaves at P2, then it goes to the intercooler and then further compressed in the high pressure cylinder and it leaves at pressure P3. So, there are three pressures P1, P2, P3. This portion shows, this is the portion which is without intercooling. Suppose if I do not have intercooler, if I directly, that means if I do not have intercooler here, state point 2 will be equal to state point 3. That means 3 will be 2 and this 4 will be 3. So, there will not be any state point 4. If we have an intercooler, so we have an inlet to intercooler and outlet of the intercooler. And this portion, this represents the two stage compression with intercooling, So, what is that perfect intercooling and imperfect intercooling? Perfect intercooling means when the compressed air from the low pressure cylinder enters the intercooler, I have told very clearly the heat is removed from this one. So, the temperature drops. If the temperature reaches the initial temperature T1, that is the original temperature before the compression in the low pressure cylinder, that is called perfect. Otherwise, if it is between the inlet to the compressor of cylinder 1 and less than the temperature at the end of compression from cylinder 1, so that is called imperfect intercooling. So, here without intercooling is this one and with intercooling is this one. So, the purple color portion which is shown here, that represents the net work saved because of two stage compressor with intercooling. This is the shaded portion represents the net savings in the work that is required to drive the compressor. So, like similar to the previous lecture in which we derived the work of compression for a single stage compressor without clearance volume and with clearance volume. Here we are going to derive the work of compression for a two stage compressor. So, it is a quite lengthier derivation, we will do step by step. So, this is let me start with this one. So, here first I am going to write the equation work of compression for the low pressure cylinder, where the pressure of the air is raised from P1 to P2. Then I will write a similar equation for the work of compression for a high pressure cylinder, where the pressure of the air is raised from P2 to P3. Okay. So, let me write this one. We will use P1, V1 the same the polytropic. We assume the process to be a polytropic one. So, which follows the law PV power n equal to constant. So, this is work of compression is equal to n by n minus 1 into P1 V1 square bracket P2 by P1 whole power n minus 1 by n minus 1. Okay. So, this is for the low pressure cylinder, where the air is compressed from pressure P1 to P2. So, this is for the low pressure cylinder, compression in the low pressure cylinder or cylinder number 1, plus. Okay. So, next I am going to write it for the high pressure cylinder, for this the work of compression for this portion. Instead of P1 V1, we will write P2 V2. Instead of P2 by P1, in the first cylinder, that is the low pressure cylinder, the pressure is raised from P1 to P2. So, we are writing P2 by P1. In the second one, in the high pressure cylinder or cylinder number 2, the pressure is increased from P2 to P3. So, therefore, the higher pressure is P3, the lower pressure is P2, n minus 1 by n minus 1. So, this will be equation number 1. This is for high pressure cylinder, Say already we have derived the work of compression. So, no need to derive these equations individually. We can start with this equation by applying the equation to the low pressure cylinder, that is the first stage compression, and high pressure cylinder. The summation of these will be the total work of compression required to drive the compressor. So, this is high pressure cylinder, that is cylinder 2, this is cylinder 1. Okay. So, now let us do this derivation. Okay. So, P2 power. So, here what I am going to do is, assume the equation which we have written is for the polytropic process, which obeys the law PV power n is equal to constant. Now, to make the derivation little bit simpler, let us assume an isothermal process. isothermal process has the least work of compression among all the three processes, like when we compare with isothermal, polytropic or isentropic. So, just to explain you this concept, suppose if you have a PV diagram like this, if you have a PV diagram like this, see, suppose, let me explain this one without clearance. So, suppose if this is the, let me use the same number which I used for the previous one. This is suction 1 to 2, then 2 to 3 is discharge, this is discharge. So, just to explain the power required to drive the compressor for the three process, I have taken a compressor, a single stage one without clearance. So, this is so there are three lines here I am marking. Okay. So, let this be 2 dash. So, let me erase this portion. Let this be 2 dash and this be 2 double dash. Let me redraw this one. So, because the letters are not clear, let me redraw it again, then we will mark the points. So, I have plotted three processes here. So, this is state point 2, this is 2 dash, this is 2 double dash. Arrow mark is this one, okay, three process. This is isentropic process or reversible adiabatic process, PV power gamma equal to constant. And the second, this one is isothermal process, PV equal to constant temperature process, and this one is polytropic process, PV power n equal to constant. So, if you see this graph, the work required to drive a compressor in case of a polytropic process, it is lying between an isothermal process work done and the isentropic process work done. That means, the power required to drive the compressor in case of an isothermal process is the least, and the power required to drive the compressor in case of an isentropic process or reversible adiabatic is highest, whereas a polytropic process power consumed by the compressor it is between isothermal and isentropic process. So, which we have seen in the previous numerical question also in lecture number 11. Okay. Now, coming to this multi-stage work of compression derivation. Okay. So, assume isothermal process, the basic equation is PV equal to constant, because it is a constant temperature process, PV equal to constant. So, for an isothermal process, so since the isothermal work of compression is the least, so we are taking this condition for an isothermal process, P into V equal to constant, P into V equal to constant. So, we can apply this equation for state 1 and 2, P1 V1 is equal to P2 V2. Now, I am going to substitute this in the previous one, in the previous equation. So, that is what I am going to do. So, substitute this one into P2 V2. Instead of P2 V2, okay, instead of P2 V2, so let us take this as equation 2. Substitute 2 in 1, substitute equation 2 in 1, we get first term I am keeping as it is. Instead of this P2 V2, I will write P1 V1. So, therefore, the work of compression is equal to n by n minus 1 into P1 V1. Okay. P2 by P1 whole power n minus 1 by n minus 1 plus n by n minus 1 into, instead of P2 V2 I will write P1 V1, P1 V1 into P3 by P2 whole power n minus 1 by n minus 1. Okay, so that is what I have written here. So, the first term remains the same, the second term everything remains the same except the P2 V2 is replaced by P1 V1. Okay. So, now we can take two terms are common. Okay. This is a common term and this is also a common term. N by n minus 1 into P1 V1 is a common term in both the summation term. So, let me take that one, n by n minus 1 into P1 V1. So, inside the bracket I will write. So, we are having this term and this term. So, first I will write P2 by P1 whole power n minus 1 by n. This minus 1 and this minus 1 I will write it at the last term, that will minus 1 and minus 1 will become minus 2. Now, I will write this term. So, plus P3 by P2, because this is whole power n minus 1 by n, minus, add both the minus 1 term will get minus 2. So, this is the work of compression. Okay. So, n by n minus 1 into P1 is a V1 is a common term. Within the bracket, the first for the first cylinder P2 by P1 whole power n minus 1 by n plus P3 by P2 for the second cylinder high pressure cylinder, minus 1 and minus 1 are added and we are getting this minus 2, getting this minus 2. Okay. So, now let us split this one. Now, I am going to split this term. Okay. Here we have got P2 power n minus 1 by n divided by 1 by P1, P3 power n minus 1 by 1. So, let me write this one. So, WC is equal to, the common term is n by n minus 1 into P1 V1. So, within the bracket I am going to split into these two terms and this also into two terms. So, the first term is P2 power n minus 1 by n multiplied by 1 by P1 power n minus 1 by n. P2 by P1 I have split it plus P3 power n minus 1 by n divided by 1 by P2. So, P3 power n minus 1 by n into 1 by P2 power n minus 1 by n minus 2. So, this is the first term which has been splitted from the previous step and this is the second term which has been splitted. P2 by P1 I have written as P2 power the subscript term, superscript term and 1 by P1 to the power of the superscript term. Similarly, P3 by P2 is P3 I have splitted and this one. Okay. Now, the objective of going for a multi-stage compressor or the primary reason is to have a minimum work done, to minimize the work done. So, we know for maxima or minima, if you have an equation, we have to differentiate and equate to 0, So, for minimum work, in this case the work of compression to be minimum. So, I am writing the minimum condition for minimum WC, differentiate this equation with respect to P2 and equate to 0. So, differentiate equal to 0. So, when we do this one, this minus 2 term will get cancelled. Okay. So, now we have to differentiate this equation. Let us keep the term which is outside the bracket, this is a common one. So, WC is equal to n by n minus 1 into P1 V1. Okay. So, we have to differentiate with respect to P2. So, here we have P2 power n minus 1 by n. So, when we differentiate n minus 1 by n into P2, the whole power of n minus 1 by n minus 1, like x square is 2 into x power 2 minus 1. So, that is a very basic differentiation. So, same thing I have used n minus 1 by n into P2 power in the power n minus 1 by n minus 1 into 1 by P1. So, that will be the same, that will be the same. Okay. So, that term will remain the same into 1 by P1 power n minus 1 by n, then plus this term will remain the same P3 n minus 1 by n into 1 by P2, 1 by P2 power n minus 1 by n, n minus 1 by n into 1 by P2 to the power of n minus 1 by n. Okay. So, that is what I have written here, n minus 1 by n plus here it is written n minus 1 by n into P2 to the power of this one, and 1 by P2 again for 1 by P2 is 1, we have to differentiate this 1 by P2, it is like 1 by x minus 1 by x square. So, this is into minus 1 by P2 square, P2 square. Okay. So, this is what you are getting here. So, this is this step. Now, we can simplify this one, n by n minus 1 P1 V1 into, take LCM in power n minus 1 minus n minus n and minus n will get cancelled. So, n minus 1 by n into P2 power minus 1 by n. So, that is what I have written here. So, this is the common term, okay, n minus 1 by n. So, 1 by P1 to the power of n minus 1 by n. So, after differentiating, okay, one step is skipped here. So, let me write this one, and this is 1 by P1 whole power n minus 1 by n plus here this term will remain the same P3 power n minus 1 by n. Okay. So, here also, okay, so one here n minus 1 by n into P2 power the superscript minus 1. So, similarly also 1 by n minus 1 by n into 1 by P2 to the power of n minus 1 by n. So, we will get a similar term n minus 1 by n into 1 by P2 to the power of minus 1 by n into minus 1 by P2 square, okay, 1 by P2 square. So, on simplification, so due to shortage of time I am just quickly doing it one. Okay. On simplifications you will get this term like 1 by P1 1 by P1 to the power of n minus 1. Okay. So, equate to 0. So, equate to 0. Okay, because differentiate and equate to 0, we have not equated to equate to 0, and after simplification we will get 1 by P1. Let us take these two terms, P1 and 1 by P1 and P3 terms are separate terms. There are two terms with P2, one is P2 and one is 1 by P2. Okay. So, 1 by P1 whole power n minus 1 by n is equal to, okay, is equal to, or let me write like this, minus P3. Next step we will take it to 0, minus of P3 power n minus 1 by n divided by P3 by n minus 1 divided by P2 square. So, if you simplify this one, so there are two terms are there. Okay. So, P2 square into n minus 1 by n we will get. So, this is equal to 0. Now, bring this term to the right side. So, 1 by P1 to the power of n minus 1 by n is equal to, this minus term I am going to the right side of the 0. So, it will become positive P3 power n minus 1 by n divided by P2 square to the power of n minus 1 by n. So, if you compare the left hand side and the right hand side, the power term is same on all this one. So, we can easily cancel that one. So, you will get 1 by P1 equal to P3 by P2 square. So, this can be cancelled. Therefore, 1 by P1 is equal to P3 by P2 square, or P2 square is equal to product of P1 into P3. Therefore, the intermediate pressure is equal to square root of P1 P3 or P1 P3 to the power of 0.5 or 1.2. So, only one step I have skipped it here. So, here if you combine these the P2 term and 1 by P2 term and 1 by P2. Okay. So, if you simplify this one, you will get in the numerator P2 power minus 2 into n minus 1 by n. You will get this one. This is what I have written in the denominator here. This is what I have written in the denominator here. So, that is what I have shown here also. See this term P2 power minus of P2 to the power of minus 2 into n minus 1 by n. So, this can be written in the denominator. So, that is what I have written in the next step. So, this is the like an optimum pressure ratio. The intermediate pressure is the square root of the inlet pressure P1 and the delivery pressure P3. So, this is a very important one. So, let this be equation number 3. Equation number, what is equation number 2? This will be equation number, this will be equation number 2. Okay. So, let this be equation number 2. So, now this will be equation number 3. The pressure, the optimum pressure which we have found out is equation number 3. Okay. So, this is equation number 2. Okay. This is equation number 2. After substituting P1 V1, this becomes equation number 2. Equation number 2, and this will be equation number 3. This will be equation number 3. What is equation 3? P2 is equal to square root of P1 P3. So, this is equation 3. Okay. Now, substitute 3 into okay, the derivation becomes a simpler one. So, when we substitute 3 into okay. So, what we are writing here, substitute 3 instead of P2 I will write P1 P3, P1 P3. So, the equation 2 after substitution substituting equation 3 into let me write straight away the equation number 4 due to time constraint. So, WC is equal to n by n minus 1. Therefore, WC is equal to n by n minus 1, n by n minus 1 into P1 V1 into P3 by P1, P1 V1 into P3 by P1. See, we have got P2 by P1, okay, P2 by P1. So, P2 is nothing but square root of P1 into P3, and the denominator P1 can be written as square root of P1 into square root of P1. So, one square root term P1 will get cancelled, one square root will get cancelled. So, that is what I have written here, and square root can be written as 1 by 2, 1 by 2. So, that is how you are getting this term P3 by P1 to the power of n minus 2 by 2n. How it becomes 2n? The square root term is written as 1 by 2 raising to the power of 1 by 2. So, already we are having n minus 1 by n. So, n minus 1 by n into 1 by 2 in the power. So, n minus 1 by 2n. So, that is what I am getting this one. This is for the square root term. This is for the square root term. So, into P3 by P1 to the power of n minus 1 by 2n. Then we are having the next term plus P3 by P1. Similarly, you get this one plus P3 by P1 to the power raising to the power of n minus 1 by 2n minus 2. And you have this minus 2. If you remember, we added minus 1 and minus 2, and placed at the last term in the bracket, so that is minus 2. Again, how I got this 2n? The pressure 2, P2 square is P1 into P3. Therefore, P2 is square root of P1 into P3, that is P1 into P3 to the power of 1 by 2. So, to simplify, we can write P1 as square root of P1 into P1. So, one square root term P1 term will get cancelled, and another, this square root of P3 is there. This can be written as P3 to the power of 1 by 2 and multiplied by n minus 1 by n. So, we get n minus 1 by 2n. Okay, so, this is the work of compression, this one. When you simplify, we will get 2n by, therefore, work of compression is 2n divided by n minus 1. Therefore, this simplifying further, 2n divided by n minus 1 into P1 V1 into, so these two are common term. Okay, so here if you see, these two are common, this is common, this is common. Okay, so P1 V1 into P3 by P1 whole power, P1 V1 P3 whole power n minus 1 by 2n, n minus 1 by 2n. Okay, since I have taken 2 as outside the bracket, this term will become minus 1, this term will become minus 1, and this is equation number 4, I think. This is equation number 4. This is equation number 4. Equation number 4 is the work of compression, is the work of compression for a 2-stage compressor, for a 2-stage compression process. If the number of stages are more than 2, suppose if it is 3, here I will have 3n, here I will have 3n by n minus 1 into this one, into the final pressure ratio divided by initial pressure ratio to the raising to the power of this one. If there are n number of stages, if there are capital N number of stages, capital N number of stages. So, according to the number of stages, you can substitute n equal to 2 or n equal to 3 or n equal to 4. Then the work of compression, the general equation becomes, instead of for 2 stage I am having here 2 here, for n stage we will have n by n minus 1. Let me write this, capital N is the number of stages into small n by n minus 1, okay, into P1 V1, okay, into P1 V1. P of, if it is, see if it is, if the number of stage is 2, if there are for a 2 stage, here you are having 2, here the pressure is n plus 1, instead of P2 we are having P3, here we are having n, so here it will be n plus 1, P of n plus 1 by P1, P of n plus 1 by P1 to the power of P of n plus 1 by P1 to the power of n minus 1 by capital N small n, n minus 1 by capital N small n minus 1. So, this is the work of compression, this is the work of compression. Here if you substitute, suppose if there are 3 stages, substitute n, capital N equal to 3, small n is, that is for a polytropic process it is 1.3 or 1.35, okay, 1.3, sometimes standard value we take it as 1.3, gamma is 1.4, n is 1.3. So, capital N refers to the number of stages. If for example, if the number of stages are 3, so here it will be 3n, here it will be the pressure. If the number of stages are 3, there will be 4 pressure. If the number of stages are 5, there will be 6 pressure. If the number of stages is 2, there will be 3 pressure, P1, P2, P3. So, accordingly the equation will change according to the number of stages. So, this is the work done, work of compression for a multi-stage. Okay. So, this equation is for a multi-stage and this equation 4 is for a 2-stage. So, this is for equation 5. Equation 5 is for the work of compression for a multi-stage compression system. So, with this background, let us solve one numerical question. Air is to be isentropically compressed at the rate of 1 meter cube per second, that is the volumetric flow rate is given from 1 bar and 20 degrees centigrade to 10 bar. So, the air is compressed to 10 times. Find the work of compression and the volumetric efficiency if the clearance volume is 4% of the stroke volume for a single stage compressor, 2-stage compressor, 3 stage. Also determine the percentage reduction in the work of compression of 2 stage and 3 stage when compared to single stage. Assume the density of air to be 1.2 kg per meter cube. So, let us write the given data P1 T1, okay. P1 is equal to 1 bar, P2 is equal to 10 bar, okay. Volume of air is given, that is volumetric flow rate. It is not volumetric flow rate, volume per unit time. So, VA is equal to 1 meter cube per second, 1 meter cube per second. Clearance volume is 4% of the stroke volume. So, clearance volume is V suffix C. It is given as 4% of stroke volume or swept volume. Stroke volume or swept volume is represented by the letter Vs. So, 4% is 4 by 100 into Vs, 4 by 100 is 0.04 into Vs. So, therefore, clearance volume is equal to 0.04 times stroke volume. So, this is also given. Okay. Density of air is given 1.2, density of air is given 1.2 kg per meter cube. Volumetric flow rate is given, that is for 1 second 1 meter cube of air. Okay. So, let us find the work of compression if the clearance volume is this one. For a single stage, it is given isentropically, it is very clearly given isentropically. So, it is a reversible adiabatic process where we have to use gamma, and not n. Here n is equal to gamma. So, for the first one, let us take this one. So, again see there is some. So, now let us evaluate the work of compression for a single stage, So, Wc equal to gamma by gamma minus 1. Question number, the first part of the question, single stage. Wc equal to gamma by gamma minus 1. Okay. Write the equation into, instead of P1 V1, I am writing MRT1. Okay, MRT1. I am using this form into P2 by P1 whole power gamma minus 1 by gamma minus 1. P2 by P1 whole power gamma minus 1 by gamma minus 1. Okay. So, volumetric flow rate is given, density is given, we can find the mass. Density is mass by volume. So, mass is equal to density into volume. So, the mass flow rate can be found because volumetric flow rate is given. So, density is equal to mass by volume. Okay. So, if the flow rate is given, this one m dot into v dot, or here I have taken this VA, volumetric flow rate, kg per meter cube per second is given. So, m dot is equal to rho of air into volumetric flow rate of air. Okay. So, use instead of this one gamma by gamma minus 1, density of air into volumetric flow rate of air. So, let us take this as V dot A, or we will take it as VA, no problem. It is mass flow rate into R into T1. R is the standard value 0.287 kilojoule per kg Kelvin into P2 by P1 whole power gamma minus 1 by gamma minus 1. And remember, gamma is equal to 1.4, gamma is equal to 1.4. So, rho A is given, VA is given, T1 is given, T1 is given as, I have not written the T1, T1 is given as 20 degree centigrade. So, T1 is equal to 20 degree centigrade, so converted into Kelvin, 293 Kelvin. Okay. So, here you will get it in kilowatts, not in kilojoule, because we are substituting mass in terms of kg per second, that is volumetric flow rate is in meter cube per second, density is in kilogram per meter cube and meter cube will get cancelled. So, we will get the m dot in kg per second, and into in one of the earlier problem we have got the work done in terms of kilojoule, because there we have taken ms in terms of kg, not m dot. Here it is m dot. Okay, so we substitute the values. We have got all the values, and we will get 328.7. 328.7. So the work of compression for a single is 328.7 kilowatts. Find the work compression volumetric efficiency if the clearance volume is for a single stage, 2 stage and 3 stage. Okay, so the volumetric efficiency we are going to find using this formula. 1 minus clearance volume by swept volume into P2 by P1, the whole power 1 by gamma minus 1. So, volumetric efficiency 1 minus clearance volume by swept volume into P2 by P1 whole power 1 by gamma. Relation between pressure and volume is gamma. If volume and pressure will be 1 by gamma, the power raising to the power will be 1 by gamma. P2 by P1 whole power 1 by gamma. So, P2 by P1 whole power 1 by gamma minus 1. So, all the values are given. Vc is given, that is in terms of Vs. So, Vs and Vs will get cancelled. So, 1 minus this is 0.04 Vs divided by Vs. So, Vs and Vs will get cancelled into P2 by P1. P2 is 10 bar, P1 is 1 bar, 1 by gamma is 1.4 minus 1. So, you will get the volumetric efficiency as 83.3%. Volumetric efficiency as 83.3%. Now, for the second one is we have to do the similar calculation for 2 stage. Okay. So, first I am going to find out the intermediate pressure. So, next one is 2 stage. So, the intermediate pressure is P2, which we have already derived square root of inlet pressure, that is the suction pressure in the first stage, into the discharge pressure in the second stage. So, this is equal to P1 into P3 to the power of half. Substitute the values of this one. Okay. So, here the 10 bar will become the pressure P3. In the first stage P2 is 10 bar. Here P1 is 1 bar, no change. P3 will become 10 bar, because I am doing the calculation for a suction pressure of 1 bar and for a discharge pressure of 10 bar. So, the intermediate pressure for stage 2 has to be evaluated. So, this is 1 into 10 bar to the power of 1.2. So, the intermediate pressure you will get around 3 bar, 3.2 bar, 3.16 bar. So, this is 16 bar. So, this is the value of P2. And use this equation where the number of stages, substitute capital N is equal to 2. So, 2n by n minus 1. So, sorry, instead of n you have to use gamma. This is for a polytropic process. So, the problem which we are analyzing is an reversible adiabatic process, isentropic process. So, Wc equal to, substitute capital N equal to 2, so 2 into gamma by gamma minus 1, substitute N equal to 2 in, okay, 2 gamma by gamma minus 1, 2 into gamma by gamma minus 1 into MRT1 into P2 by P1, P3 by P2. Okay. So, this is for this one. So, this is the formula. So, substitute N equal to 2 and MRT1 into P2 by P1 MRT1 into P2 by P1 whole power gamma minus 1 by gamma minus 1. So, the equation is right. 2 gamma, capital N, instead of capital N I am substituting 2 into gamma by n minus 1 into MRT1 into P2 by whole power gamma minus 1. So, you substitute the values like a similar substitution that we have done for single stage. The work of compression is 274.9. So, this comes around 274.9 kilowatt. So, here also you substitute the volumetric flow rate into density of air. So, this is for a 2 stage 274 point. So, if you see the single stage it is 328.7 and for the 2 stage it is 274.9, and there is one more stage for which we have to find out, that is 3 stage. If n is equal to 3, n is equal to 3. So, if n is equal to 3, the P2 will be equal to P for 3 stage, okay. It will be cubic root, it will be not be square root, it will be cubic root. So, P2 equal to P1 into P4. So, let me write P1 will become 1 bar, there is no change. Here P3 is 10 bar. In the 3 stage, as I said before, for a 3 stage there will be 4 pressure, for a 2 stage there will be 3 pressure. So, in a 3 stage there will be 4 pressure like, okay. So, the discharge pressure will be P4 10 bar. So, the intermediate pressure, okay, the intermediate pressure we can take it as P2 itself, no problem. So, this P2 is equal to cubic power of, that is 1 by P1 into P4 to the raising to the power of 1 by 3. P1 into P3 to the raising, instead of 1 by 2 square root, instead of 1 by 2 you have to take the cubic root, okay. P1 into P4 into this one. So, here it is P1 into P3 square root, here it is P1 into P4 cubic root. So, you get the intermediate pressure as, if you calculate 2.15 bar, 2.15 bar. Again, now substitute capital N is equal to 3 for a 3 stage system, the work of compression, substitute N equal to 3. So, what is this equation? Equation number 5. Okay, let me write that one so that it is easy for you to refer later. N equal to 3, substitute N equal to 3 in equation 5. Here substitute N equal to 2 in equation 5. So, that is what I have written here. So, this is very important. So, when you substitute you will get 3 gamma by gamma minus 1, okay, 3 gamma by gamma minus 1 into MRT1 into P2. Of course, P2 the intermediate pressure I have taken this one. So, for the third stage we are getting 259 kilowatt. So, still it is less than the 2 stage work of compression. Similarly, you can do the volumetric efficiency for this one using this formula, okay, using this formula, only the pressure ratio varies. So, it is 94.9 for the 2 stage, 94.9 percentage. Please we can use this same formula, only the pressure ratio will vary, and similarly for this case the volumetric efficiency is equal to around 97 percentage, 97.1 percentage. So, the percentage reduction in the work of compression, when we compare 2 stage and single stage, it is there is a net saving in the power consumed by the compressor, that value is 16.4 percentage. When we compare the 3 stage work of compression with the single stage, it is little over 20%, that is 21.2 percentage. Okay. So, to summarize, we have seen the objective of the development of a multi-stage compression. What is the perfect intercooling? Imperfect intercooling. In intercooling, the temperature of the compressed air is brought to the initial one. If that inlet temperature before low pressure cylinder compression is achieved, it is called perfect intercooling, otherwise it is imperfect intercooling. So, the main advantage of going for a multi-stage compression is to minimize the work done on the compressor, that is the power required to drive the compressor. We have seen one numerical question comparing the power required to for the same operating condition, what is the power required for a single stage, 2 stage and 3 stage, and we have seen an improvement in the saving of the power requirement for 15%, 16% between single stage and 2 stage, and between single stage and 3 stage it is around 21%. So, with this I conclude the lecture number 12. Thank you.